Welcome back. It's Monday, so we have another Wise Guys segment. Paul, what are we talking about today?
So we've been talking a lot about light waves. Today we're going to talk about sound waves instead and whistles. How do whistles work? And I got this super fun toy that we will play around with a little bit at the end. So if we go to the first graphic, sound waves are just oscillations in some pressure. And if we plot them as a function of time, for example, if I have a single tone, it'll just oscillate up and down, for example. And the distance between the two peaks, that's called the period. And if you take 1 over that period, that gives you the frequency of the wave. If you have waves that have a big amplitude, they'll be louder than waves that have a smaller amplitude. So today we want to look at whistles. So if I go to the next slide, you know, we're all familiar with different types of whistles, police whistles or referee whistles or the kind of straight whistle that we have here. And how they work is actually a little bit complicated. So if we go to the next slide, you know, I have, for example, in the upper left, I see that the air is coming in from the left-hand side, and it's going to kind of loop around and interact with itself as it's going in. But the thing that makes it complicated is that on the lower left, we see that when we blow against this little wedge, I actually get some of the sound going up, some of it going down, some of the air is going up, some of it's going down. There's a lot of turbulent flow. But basically, we can think about it if I have some air pulse in the upper right now going in this whistle, and it comes in from the left, and it's going to circulate around that ring, and then when it comes back to the entrance, it's going to deflect some of the air that's coming in. So it's going to interact with itself, and that's just going to happen over and over again. There's going to be these air streams fluttering against each other. And you could ask, well, how often is that going to happen? Because that's going to set what does the sound like. And so if we go to the next slide, that's going to be determined by how long does it take for an air pulse to go around the circumference. So if the cylinder has a diameter of about 3 centimeters, it has a circumference of about 10 centimeters. Sound goes at about 340 meters a second, and so you can easily calculate it takes about 0.29 microseconds to go around, and that corresponds to a frequency of about 3,400 hertz, which is a pretty high pitch. That would be like the referee whistle. If instead we had something that was only like 500 hertz, that frequency corresponds to a 2 millisecond period, so quite a bit longer, and that's how in 2 milliseconds sound can go about 27 inches. So if we come back to us then, so first of all, what does 500 hertz sound like? This is a 500 hertz tone. Hopefully you can hear that. Yes, maybe. Okay, and what I happen to have here is just a whistle. So it's got an input and it's got this little wedge right here. And this turns out to be about 13.5 inches. And so if I make air pulse here, it's going to have to go out and back. So that's about this 27 inches, which is exactly the same sort of pitch that we heard. If I blow a little harder, so the air is going a little faster, then the pitch actually goes up a little bit. Okay, but I want to come back to this kind of special whistle that I was given. It's a little bird that you can see, and it's got a little different because it's got a hole in the top, and I've actually put some water in it. And I'm just going to have you give that a good little blow.
It sounds like a bird.
Yeah?
Cute.
Yeah. So what's going on? It's not just a constant whistle. Go ahead, you can do it again. Yeah, so it's kind of warbling, and the reason is that because it's filled with water, it's going to be the same sort of thing that if I blow air bubbles into this, it's bubbling up the water. So if we go now to the last slide, this is a picture of like what might be going on inside. When we're blowing into it, I'm blowing bubbles into this, and it's changing the shape of the cavity because the water is moving around, and it's doing that in a very kind of chaotic way, and that's why we're getting this different kind of a warbly pitch that comes out of the whole thing. So in fact, if we come back to us here, we can show that that happens. I'm just going to dump out the water. Yeah, and there we go. And now if you give the blow, it's going to be very different. Yeah, it's just this high pitch. We're not getting this warbling sound because now there's no longer water that we're trying to bubble things through.
Yeah.
So we will pick up with more whistles next time, maybe for a holiday special, have some fun stuff to look at there.
Did not know that you could have all of these different whistles and they can all sound different.
Indeed.
Awesome. Thanks so much, Paul. We'll see you next week.
Thank you. Bye-bye.